Michelle.
No, my brother's friends are making fun of me.
Brother?
I know, I'm so sorry. I'm giving that to you. So I just need it.
Jenny, you should have.
I was like, I'm sorry.
Yes, you do. It's in Boston. I thought it was in Ohio for a long time. Maybe that's no Northwestern's in Ohio.
I don't know.
Whatever. It's like right Ohio.
Oh my god. Oh, it's in their head.
Jeez, man.
Leave you do your stuff on graph paper, that's perfectly fine, that's not necessary.
I'm really sorry, it's a 15-minute walk.
Then I'm learning dusting away from the guitar. It's really fun. Yeah, we did that too for a long time here.
Romance on the phone. It's weird classic vibe. No. There's no word, it's just all guitar.
Are you a singer?
Yeah. So I hate that. Singer-songwriter stuff. Nothing
That doesn't make any sense.
Yeah, like everybody else.
yeah, it's Donna. I love
He was all like,
stuff that's
Like
not,
individual people.
yeah, it's not that, like Edward and stuff.
I see those separately.
Yeah, it's not like fans.
I see what you're saying. I like got some of those Jack Robinson, so I like tried to that
you think they're gonna waste money on jazz, right?
All right, let's go ahead and get started, please. Take out your notes. So last time in class, you were introduced to the following expressions. These are the kinematics equations for a one-dimensional motion with constant acceleration. First of all, position as a function of time. Velocity as a function of time. As we saw with my second example at the very end of class last time, if you algebraically combine these equations together, you will arrive at the third kinematics equation, which is as follows. Okay, here at the beginning of the period, we're going to finish our basic practice of the use of these equations, because as I said last time, the more you use the equations, the more you understand exactly what it is that they're saying. Now, when I did my two major examples at the end of class last time, both of those situations were rather straightforward. We'll begin today with something a little bit more complicated. I'll take a look at the problem here on the screen. Hopefully you won't have this happen. police car stops at the light. The speeder, traveling at a constant velocity of positive 40 meters per second, passes the police car. At that instant, the police car accelerates at positive 5 meters per second squared. When, where, and with what velocity does the police car overtake the speeder? So hopefully you're not the speeder in this scenario. Now, as you begin to copy down the problem, notice immediately that the problem gets a little bit more complicated in the following sense. In this case, there are two objects, whereas in the previous examples that I did last time in class, it was just a single object. The rocket in that first example, and then the car slowing down in the second. When you are given a more complicated situation, such as this, what you do is you break it down into a series of manageable parts. What we'll do is we'll take a look at the speeder first, describe that completely. And secondly, take a look at the police car, describe that completely. And then once we've done that, we'll look for a means of linking the two objects together. Now, I erased, by the way, the third kinematics equation from the board here. It turns out that we won't need it for this problem. Now, as I said, we break this problem up into a series of manageable parts. Let's just take a look at the. You all right? Yeah. Let's just take a look at the speeder first, all by itself. So, like we saw last time in class, you begin a basic problem. Remember, I'm always drawing out a diagram. So, very simply, the speeder starts here, and then eventually, when it gets overtaken by the police car, it will be over here somewhere. Okay, now what do we know about the speeder's motion based upon what's given here in the problem?
Constant velocity, 40
Okay,
meters
yeah,
per
it's
second.
a constant velocity of 40 meters per second. That actually means three things. It means, first of all, that the initial velocity of the speeder, we'll call it v naught speeder, is 40 meters per second to the right-hand side. That's what the plus sign means. It also means that the final velocity of the speeder, that the speeder, is also equal to 40 meters per second. But even though it doesn't explicitly say so, it also tells us what the acceleration of the speeder is. The acceleration of the speeder would be what?
0.
0, because it's a constant velocity. So we note that the speeder is 0. Incidentally, as we saw last time in class, usually in situations such as this, we assume that the person starts at the origin. So that right here, we'll say is the origin. We'll say that x naught for the speeder is equal to 0. In a few minutes, by the way, for the police car's initial position will be equal to 0, because that's how the problem is defined. The problem is defined such that the problem starts when the speeder passes by the police car. Okay, now before we get to the police car, however, there are two things that are unknown here about the speeder, and they would be what? What's unknown about the speeder? The distance that it travels when it eventually gets overtaken by the police car. Yes, the time is unknown as well. Okay, then before we get to the police car, let's just write down the equations as they're applied to the speeder. I'll do that here in a moment. So first of all, my top expression, position equation. Notice in the position equation here, the two things immediately are 0. The initial position of the speeder x naught is equal to 0, and its acceleration is equal to 0. So I only have here the middle term when we apply it to the speeder. I only end up with the following expression. Notice that there are two unknowns in that expression, and that's the position x and the time t. Notice also, by the way, that the second equation, when I write it down for the speeder, is actually no help whatsoever. The reason for that is that Remember that the acceleration of the speeder is equal to 0, so you just have v naught and v is the same thing. Mathematically, of course, that doesn't help us, so frankly, I'm not going to even bother writing it down. So this equation by itself right here with two unknowns as applied to the speeder is obviously not enough information to solve the problem, which then means that we, of course, have to look at the police car. Now let's jump back up to the top board. And let me now describe the police car. The police car begins at the origin as well. After all, that's how the problem is defined. The problem starts when the speeder passes by the police car. X naught here is equal to 0 as well. And then, even though we don't know what it is as yet, the final position of the police car over here is the same as the unknown final position of the speeder from earlier, because, once again, that's how the problem is defined. The problem ends when the police car overtakes the speeder. Now, in addition to the position here being unknown, the time necessary for the police car to go from here to here is the same as the time necessary for the speeder to go from here to here, even though we don't know what that time is as of yet. Once again, this is how the problem is defined. Okay, what are, however, the known quantities about the police car? We know a couple of things about it. We can give me an example of it. Okay, the acceleration of the police car, I'll call it APC. It's 5 meters per second squared to the right-hand side. Okay, what else do we know about the police car, Ryan?
The initial velocity is 0.
That's right, police car starts at rest. So we'll say V naught police car, we'll call it, is equal to 0. And then lastly, we have the final velocity of the police car. Can I just assume that the final velocity of the police car is 40 meters per second, the same as the velocity of the speeder? When the police car overtakes the speeder? No, it's completely unrelated to it. As we'll see, the final velocity of the police car, when we eventually solve the problem, is actually going to be a lot larger than 40 meters per second. So now I've got the quantities associated with the police car here described. Now we write out its equations. Okay, first of all, the position equation above. In this case, once again, two things are equal to 0, but it's the first term, x naught, and the initial velocity here in the second term, which for the police car is equal to 0, because remember, so the position equation then is just the acceleration term here for the police car. So, and then we have the velocity equation for the police car, where yes, the velocity initially for the police car is equal to 0. So this second equation simplifies to become this. So this is easy. And what we essentially have here now is three equations and three unknowns. The three unknowns being x, t, and the final velocity of the police car. Now, algebraically, when you say three equations and three unknowns, that implies that the algebra may be a little bit messy. In this case, however, it's not. What I have to do is I have to somehow link the two objects together. The easiest way to do that is to note that, yes, the final position of the two objects, remember, is the same. So algebraically, let's begin with just setting these quantities equal to each other. So I have the quantity for the speeder equals then the quantity for the police car itself. And now if you take a look at that expression carefully, what is the only unknown in that expression? Yes, time t, so I can solve for it. Now notice that it's a quadratic. So technically speaking, how many solutions are there? There's two solutions. If you look carefully as well, what is one of the solutions for time here in this equation? 0. Notice that that does make sense. At time t is equal to 0, the position of the speeder and the position of the police car is the same. We don't particularly care about that, however. We're more concerned with what happens over here. So what I'm going to do algebraically is just cancel a t from each term like so, and then solve for the remaining time. I just cross multiply. So cross multiply the 2 and the acceleration of the police car to the other side, thereby arriving at the following expression. And now I just plug in my numbers. So numerically, this is going to be 2 times 40 and then divided by 5. So 2 times 40 is 80 in the numerator, divided by 5, and that then gives me a time of 16 seconds. Okay, now that I know what that time is, Let's jump back here for either the position of the speeder or either the position of the police car. Doesn't matter which of the two expressions I use to find the position X. No, so the same thing. This one is a little bit easier to do, however, because it's nothing more than 40 meters per second multiplied by 16 seconds. So I still have 16 here in my calculator, multiplied by 40, and that comes out to be 640 meters. So that's the position where the police car then overtakes the speeder. And then lastly, we can now find the final velocity of the police car because it's nothing more than 5 meters per second squared multiplied by the time of 16 seconds. 5 times 16 is 80 meters per second. So as I said earlier, the police car, when it does eventually overtake the speeder, is actually moving at a pretty good clip compared to the speed that the speeder itself. Okay? Nice little problem to warm up today with. Anybody have any questions about this?
So you know how this car you use in those equations? Why did you do that with the speeder?
Okay, the reason why I didn't do that with the speeder is because the second equation, when you apply it to the speeder, doesn't really tell me anything. Because the acceleration, remember, the speeder was 0. So this term isn't here, it's just speed is equal to v naught. It's just a constant velocity. Mathematically, that doesn't help me. Okay. Okay, now, last time in class, when I defined for us mathematically the kinematics quantities, I said that velocity is the derivative of position with respect to time, and I said that acceleration is the derivative of velocity with respect to time. And in just a simple conceptual way, I went over the basic idea of derivatives using some graphs. But then, since then, we haven't seen any graphs at all. We've been talking about problems algebraically, solving for whatever it is that we're looking for. How do we kind of link the two together, reinforcing in your own minds exactly what is meant by the derivative? The way that we do that is to take examples like these and actually graph out the quantities themselves. Let's take a look at an example of that in the following way. Now, after I completely run through the solution to this problem, I'm going to ask for a volunteer. I'm going to ask for a volunteer to actually walk this problem, walk the motion. Let's see if anybody can do it. Nobody can do it in chip period 2. Nobody can do it in period 4. Let's see if period 6 is better. That's the negative side of this. So a car moving at plus 10 meters per second, so initially that's to the right-hand side, undergoes an acceleration of negative 2 meters per second squared for 10 seconds. Then the person accelerates at a totally different value, positive 1 meter per second squared for an additional 5 seconds. What we're supposed to do is graph the acceleration, velocity, and position as a function of time, and then somewhat cryptically at the end of the problem, label any vertices that occur on the position versus time graph. Let's see what that means as we get deeper into the problem. Notice that because there are two discrete values of acceleration, we have to break the problem up into two time intervals. Essentially what we have to do is, using our two basic expressions, is calculate. We have to calculate the position and the velocity of the object at the beginning and end of each time interval. Once I have that information, once I have that data, if you will, that's then when I construct the graphs. And as you see, you always graph in a very specific order when approaching a problem such as this. Okay, let's take a look at the first 10 seconds of the problem. So from 0 to 10 seconds. And here's the data associated with this time interval. We'll just arbitrarily start the object at the origin like so, and the initial velocity v naught is given to us as plus 10 meters per second. The acceleration is negative 2 meters per second squared, and the time interval itself, t, is 10 seconds long. Using this information, just using this data, all that I have to do with my equations is calculate the position and the velocity after 10 seconds. So there's really no algebraic manipulation that I have to perform here. All I have to do is plug these values in to get these respective expressions here and find the final position and final velocity after 10 seconds. The reason why I need those numbers is that those numbers will then become the initial values of the position and velocity for the remaining 5 seconds of the problem, and then recalculate again. So here's then how I go about doing that. As I said, I'm going to calculate two things: position and velocity. So first of all, the position, here's how the numbers work. 0 plus 10 times 10 plus 1/2 times negative 2 times 10 squared. Let's see what we get. So 0 first, and then 10 times 10, which is 100, plus 1/2 times negative 2 times 10 squared. And I end up with something a little bit strange. I end up with the final position is 0. Now wait a second. The initial position was 0 and the final position was 0, yet the object was moving to begin with. What must have happened to the object in terms of its motion at some time during this time interval?
Slow down. Stop.
And did what? Turned around and moved back in the opposite direction. We will eventually have to figure out when and where that happens. Next, let's calculate the velocity here after this time interval is going to be nothing more than the following. 10 plus negative 2 times 10, so 10 minus 20 is negative 10 meters per second. Notice the negative sign. This means that yes, the object is moving in the opposite direction from where it was originally moving. So, at the beginning of the interval. Now we look at the remaining 5 seconds of the problem, from 10 to 15 seconds. The final position for the previous interval, that now becomes the initial position of the next interval. I'm not arbitrarily setting the initial position here equal to 0. I'm specifically saying that the initial position here is the final position for the forward. Similarly, the final velocity from the previous interval is now the initial velocity for this interval. And then we also have the following data from the acceleration, is 1 meter per second squared, and the time interval t is 5 seconds long. Using this information now, I just plug everything into the equations to find the final position and final velocity. So this is the remainder of the calculations that I have to do prior to starting the graphing. Now numerically, here's what happens. First of all, position-wise. X naught, which is, yes, 0. And then it's going to be plus negative 10 times 5, so negative 50. And then plus 1/2 times 1 times 5 squared. So plus 1/2 times 1 times 5 squared. And that comes out to be negative 37.5 meters. So overall, the object ends up to the left-hand side of the origin, 37.5 meters away. And then final velocity. Final velocity is going to be first the initial velocity, negative 10 meters per second, plus then 1 times 5. So negative 10 plus 5 is negative 5 meters per second. So calculating out these quantities here for the 2 different time intervals is fairly easy to do. There's no algebra involved. We just plug everything in. And now we start to construct our graphs. When you graph, you always graph in a very specific order. You graph acceleration as a function of time first, because acceleration is the derivative of velocity. And then you graph velocity as a function of time second, because velocity is the derivative of position. And then lastly, you graph position. Here's then how this works. Okay, now I'm just sketching my graphs here, but you do want to be careful as you sketch. With acceleration in meters per second squared as a function of time t in seconds. And we're looking at a 10-second time interval to begin with, and then an additional 5 seconds. Okay, take a look on the top board at the first value of acceleration. It's a constant, negative 2 meters per second squared. What does the graph of a constant look like?
line.
It's a horizontal line with a slope of 0. So right here, for example, we'll say is -2 meters per second squared. We have a constant acceleration at that value. Okay, then in the second interval, we have another constant, positive 1 meter per second squared for the remaining 5 seconds. So right here, we'll say is positive 1 meter per second squared, and then right here is our constant value. Notice that you end up with a rather strange looking piecewise function or a discontinuity. And because you all have sat in various math classes here at the school, you may be wondering to yourself, is this an open point or is this a closed point, etc.? Remember all that stuff that you looked at with discontinuous functions in math class? Well, what happens here? Let me ask you this. Is it physically possible for an object to literally in an instant, no time interval at all, to instantaneously go from an acceleration of -2 meters per second squared to positive 1 meter per second squared?
No.
Is that physically possible? No, it's not. So what actually happens? Don't draw this. What actually happens is that over a very small interval of time, in a smooth manner, the acceleration changes from a value of -2 meters per second squared to positive 1 meter per second squared. There's some smooth curve polynomial that describes this. But notice that right here, over this short time interval, the acceleration is changing. It's not constant. That's mathematically difficult to describe. When you are taught introductory physics, you are always taught, as you guys are now, the simplest possible situations first, the idealized situations. The reason why we teach that to you first is because it's usually the easiest situations to handle mathematically. Once you understand how to handle that mathematically, then we start adding layers of complexity to situations, ultimately then approaching the real world and the description of it. So is it physically possible for a car, for example, instantaneously go from -2 meters per second squared to 1 meter per second squared? No. This is what actually happens. Mathematically describing this is difficult to do, so basically we ignore it. So to just kind of summarize that little spiel there, essentially all that happens is you end up with this rather strange, discontinuous piecewise function, and that's perfectly fine. So, as I originally drew. So we don't have to worry about closed points and open points and all that nonsense that they drill into your heads like simple in the mathematics class. And we don't care. It just says like that. Okay, next. So velocity is a function of time. So 10 and then 15 seconds. Take a look at my first set of numbers. Velocity goes from a value, say right here, positive 10 meters per second at the origin, to then say right here, negative 10 meters per second after 10 seconds. But now the question is this, what actually connects those 2 points? Well, take a look at our equation. Here's the velocity as a function of time. What type of graph is that equation representing? Look at our equation right here. If we graph velocity as a function of time, as I'm starting to do, what type of graph is sketched out by that equation? It's linear, that's right. Think of it as y equals mx plus 8. It's a line. The slope of the line is the acceleration. So, here's where the idea of the derivative comes in. On a velocity versus time graph, the slope of the tangent line is the instantaneous acceleration. Think of the tangent line as the slope of this ruler's edge. Notice that the slope of this ruler's edge here never changes over this 10-second time interval. The slope of the ruler's edge here is the constant acceleration of -2 meters per second squared. This is literally the derivative of this. Notice, by the way, what else happens. Notice that my line right here crosses the axis. At this instant in time, the velocity is 0. It's going from a positive value of velocity to a negative value of velocity. So So in terms of its motion, what is the object doing at that moment when it's at rest for an instant? It's stopped, but it's turning around and moving in the opposite direction. This right here is a turnaround point. We have to figure out when and where this happens. Now, just by looking at the symmetry of my graph here, when this happens is probably pretty obvious. What time do you suppose this is?
5 seconds.
5 seconds. Here's how you show it. Let's figure out where that line crosses the axis. Well, right here at this instant, right here at this moment, the velocity is 0. So let's look at our velocity equation where I set the left-hand side at v equal to 0. Now all I'm going to do is solve for t. So move the v naught to the other side, divide by the acceleration a, and that then gives you this. Now here's what happens when I plug in my numbers. I'm going to have here negative and then v naught. That's 10 meters per second, divided by the acceleration, slope of this line, which was negative 2 meters per second squared. So negative 10 over negative 2 is 5 seconds. It's this point here. So, but then lastly, for my velocity graph, over the remaining 5 seconds of the problem, the velocity goes from negative 10 meters per second, that's this point right here, to negative 5 meters per second. So negative 5, we'll say, is about like that. So right here is negative 5 meters per second. And once again, connecting those 2 points, it's a line. The slope of this line is the acceleration. Specifically, it's 1 meter per second squared. Once again, I know this because of the idea of the derivative. Slope of the line, slope of the ruler's edge, slope of the line that is tangent to the curve on a velocity versus time graph is the instantaneous acceleration, in this case of 1 meter per second squared. So literally, this right here is the derivative of this. Lastly, you've got right there a point of discontinuity. That point of discontinuity corresponds to what's going on here instantaneously as we go from one acceleration to the other. In reality, is that point of discontinuity there? No, it's some smooth curved polynomial, something that kind of looks like that as we go from one value of acceleration to the other. We'll be able to look at detail. And then lastly, usually what's most difficult of all is graphing out the position as a function. So position in terms of meters. And then we look at 10 seconds and then eventually 15 seconds, like so. Now let's take a look at our data from here on the top left-hand side of the board. The object started at the origin and it ended up at the origin after 10 seconds. So it started at the origin, ended up at the origin. So now the question is this: what type of graph connects those 2 points? Somebody said it. It's a parabola. The reason why it's a parabola is because we're graphing position as a function of time, when we're graphing a quadratic equation. In order to graph a quadratic equation is a parabola. In which direction does the parabola open? Downwards, because the quadratic term is a negative. Parabola has to look like this. We have a vertex of the parabola right here at 5 seconds. The reason for that is as follows. It has to do with the derivative. On a position versus time graph, the slope of the ruler's edge, the slope of the tangent line, is the velocity. So watch what happens right here at the origin. Notice the slope of the tangent line right there is a positive number. Specifically, it's 10 meters per second. And then the velocity goes from 10 meters per second to 0 right here at 5 seconds. Notice that the slope of the ruler's edge is equal to 0. Velocity goes from 10 to 0. And then it goes from 0 to negative 10 meters per second right here at a time of 10 seconds. It goes from 0 to negative 10 meters per second. This line right here is literally the derivative of that parabola. The last thing that we don't know, however, about that parabola is where is the turnaround point? Where is the vertex? We now have to find it. find the vertex, we just do the following. Right here, we set our x naught equal to 0. Remember that our velocity at that moment was 10 meters per second. The acceleration, remember, over this time interval was negative 2 meters per second squared. And now I set the time t equal to 5 seconds. And all that I do is I take these numbers, I take this data, and plug it into the equation on the top board to find the position x. That will give me this turnaround point. Let's see what I get. It should, of course, be a positive number. So I have x naught, which is 0, and then v naught times t, so 10 times 50, or 10 times 5, is and then plunge 1/2 a times t squared. So that's 1/2 times negative 2 times 5 squared, and that comes out to be a position of 25 meters. That's this one here. And then lastly, we go from 0 to negative 37.5 meters after a total of 15 seconds. So let's see, negative 37.5 meters is kind of down here somewhere. So we go from this point here to this point here. And what type of curve connects those 2 points? It's a parabola. In which direction does the parabola open if the acceleration is a positive number? Upwards. Do we come to another vertex of the parabola?
Yes.
Don't. The parabola looks like this. It's a piece of it. How do I know that? I know that because of the idea of the derivative. The position, which is time graph, is slope of the tangent graph, is the velocity. Right here in 10 seconds, the slope of the tangent right there is negative 10 meters per second. Now watch what happens to the slope of the ruler's edge. It goes from negative 10 meters per second to negative 5 meters per second. So that's this point right here. So this right here is the derivative of this. And now lastly, we need a volunteer. Who thinks that they can walk this problem? Who thinks that they can do it? It's like being at the circus. You don't want to be called on by the clowns, right? All right, I'll go ahead and walk the problem for you. So let's think of it like this. Let's say that right here is the origin, the edge of the desk. But remember in this problem that I'm already moving to the right-hand side at 10 meters per second when the problem starts. So what I have to do is I have to walk up to the edge of the desk, and then the problem starts. So now watch my motion, keeping in mind the parabolas over there on the right-hand board. The problem basically looks like this. Ready, set, go. Go out 25 meters, turn around in the opposite direction, pass the origin, and then slow down to 5 meters per second. Boom. The problem ends right there. 37.5 meters to the left-hand side of the origin, moving in that direction with a speed of 5 meters per second. You want to see it again more smoothly. Everything just looks like this. Go. 25 meters. Slow down. Problem ends right there. So all of that just to describe me walking back and forth in front of the desk. I told you that describing motion wasn't trivial. In order to describe motion, differential calculus is necessary. So let's take a look at practice. Yeah, that was this parabola right here. Start at the desk, walk forward, turn around, and ended up at the edge of the desk. And then move to the left-hand side of the desk, slowing down as it did. Huh?
No.
Yep. I got that from the data above. So I'm using the data. Think of it that way to construct the graphs. That's what you got. All right, take a look at the 2 problems on this handout. They are obviously examples such as this. What I'm going to give you an opportunity to do right now is work together on the first problem. Kind of like what we do in review sessions. I'm going to give you about 10 minutes or so working together to start to write out the solution to the first problem by exactly using the method that I did here with my example. And then after you've got a chance to start working on the problem, kind of check your work as you go, what I will then start to do is I'll start to lay out the solution to problem number 1 here on the board. So essentially, we're going to do problem number 1 here together, and then later on as homework, you'll be able to complete problem number 2. So go ahead and start working together on this example, and in about 10 minutes or so, I'll start running through the solution on the board. Yeah, you can do it on this, it's perfectly fine. Okay? So go ahead and get started. Super. Always.
I really want like
I get frozen yogurt. I could get it. It's much.
these last 5 minutes of my life I didn't have. I don't know. It's so bad. It's just the heat. It's like,
I'm not gonna do
right down.
So the first thing you do, like I did on the top board, is calculate.
Ooh, okay.
Bless you. Are you drawing this? Not yet.
Equals 0, right?
Yeah.
Okay. What else? V naught equals, okay, so the initial velocity is 20 meters per second.
Now notice that it says constant velocity for the first 5 seconds of the problem. So what is the acceleration?
Acceleration is 0. A equals 0.
I'm the car accelerates. So second 5 seconds. Can we integrate this to get the? Can we integrate the acceleration to get the velocity?
Yeah.
Is that what we're supposed to do?
No. He's like, I mean, yes, you could.
We also have to take into account like the initial velocity, it's like C.
C. Oh my gosh. This is actually helping me out right now. X.
You like casually?
What?
Casually.
Oh, okay, so X equals, so let's find X first.
Wait,
So
like,
X,
what else?
that was a
what
fun
else- what do we know about this?
we have to, we have to do the first one. We can do the second one. Okay.
What I've been doing.
X equals, oh god, is it a calculator? I have a calculator. Got this. Got this.
Crap. I always start off on a good note. You're going, oh, my colors, they're going. And then it just goes to shit. I wish I had this class in the morning.
Just 20 times 5.
This is what something. And then what are the 2 equations that we have?
20. Okay, so meter per second T.
20.
Oh, yeah.
Oh shit. Holy crap.
So X0 is 100, right?
Yeah.
B0.
Right, it's just 1 times 5 because the 0.
Oh, the second one.
X0 is 100.
Yeah.
A equals
0.
No.
For the
X
first one.
equals 100, not X.
Yeah, but then remember you take that
Right, for
position
the second
five.
one.
Yeah, for the second one.
Oh my god. Sorry if I do.
Then what about
Don't
B?
hate me. B is 20.
B or B not?
B. B not. Yeah, B not. Sorry for a second. And then T equals
Sounds like a
5.
drill boss, so I want more yet.
X equals,
Nope. I always wear long sleeves. There's only 2 days out of the year where I'll wear long sleeves.
I oh god, that felt so good.
Halloween is the only day of the year where actually
I totally just-
work at actually end.
Oh,
This is
I
the
gotta go live it. Let me
Halloween is
figure
the
out.
only day of the year where I work at And then after that, the only other day that you'll see me in short sleeves.
Same problem. I've no comprehensive brain right now. I'm like, I feel like if I could do anything.
Okay, now I'm going to erase the examples here on the board. You have it in your notes. Erase the examples here on the board. Very slowly start laying out this problem. Oh,
How do you find X? That's very vague statement. Which one are you talking about? Vague statement. What?
That's a very big statement.
For the first one,
I just want to say it.
plug in
Yeah,
X naught, which is
Wow,
0,
I'm gonna get it.
V naught, which is
Oh, you guys haven't done it
20.
yet?
No, I wrote it out. Okay, it's
Wait, what is X here?
plus
Oh, they do.
Oh, yeah.
Okay, then 1/2 of negative 25.
0.5 times negative 25. 187.5.
Wait.
X equals 187.5.
No, X equals 100.
What? No, final X. X naught.
Negative 5. T again?
5.
It's 5
So you did this, right? You have 20 times 5 plus 1/2.
They're in meters.
Yeah.
We're just
So
doing
A
basic.
equals 0, right?
Second one?
Yeah.
Because isn't it
No,
20
no, wrong.
20. Oh, yeah.
plus
Negative
negative
5.
5?
Wrong.
What's wrong? Who's wrong? V is wrong? Or X is wrong?
X.
No, it's not.
What's that?
That's not doing this.
Okay. So it's 100.
Oh, we forgot the square.
Yeah, you got
There's a
it.
square.
T squared. So 5 squared is 25.
25
Times negative 5 divided by 2.
Yeah.
Why did it make 0?
Because 1/2.
Yeah, 1/2.
So
Okay, what's our
negative,
answer?
then you get X equals 100 minus 62.5.
37.5.
Yeah.
37.5.
Sorry, thanks Henry. Catching
Okay,
our
but then it
mistakes.
says lot. So it doesn't make
Acceleration,
sense.
velocity, position, as much
Wait,
as
now I need
time.
one more. There we go. Velocity.
No,
Right, did that. It's negative 5.
Yeah. Do that one.
So now just graph it.
Yeah.
For how much?
No, how do you do velocity?
No.
No, we. Mr. Shaw,
Yes.
they're going to be on 3 separate graphs, correct?
Yes. Now, you can just sketch the graphs like I did, and incidentally, if you want to borrow a ruler to help you do that, you can certainly do
I
so.
got a roll.
But it's not necessary to do them on graph paper, you can just sketch them neatly like I did.
How many gives us again?
So we have
Go
5
ahead.
and 10
Oh, hey, I
seconds.
just found a $20 bill.
Can I have it?
Oh, wait, no. That's not
No.
I was looking for a ruler.
I swear.
We're ready. Alright, so
Okay,
initial
So acceleration.
acceleration is 0, right? And then it goes to, it's 0,
Let me split up the chart. So
Wait, so at 5
5
it's
and
0.
10. So it's at 0,
Then at 10 it's negative 5.
wait, no.
so 0, negative 5. So it's that.
You may want to check your numbers for the two intervals against
0
mine.
from
A is 0. A
A
is
is 0,
5 seconds.
acceleration in meters squared, meters per second squared,
And the second one is
and
5. So
then
then
t of s. So from,
Why are you at negative 5?
because negative, it switches,
it's not a negative.
yeah, it
It's
is.
at 0. The acceleration
No,
is 0.
from 0 to 5, and the second one, it goes from,
Yeah, oh yeah. Oh, I do.
Oh, because the acceleration is negative. Sorry.
yeah. I know.
Wow.
Thanks, I do that.
I'm sorry?
So then what's this? 10
Velocity
on.
of meters. Wait, no.
10
Wait, the problem ends. Oh, Nash is just rolling.
Yeah. Yeah. Gosh.
Nash, you're just like, oh, dang it, I was gonna. It's good. It's all good. Oh, why is this graph so big?
Acceleration.
Alright, so
check your calculations
velocity
against mine up there on
initials
top
are
board.
20.
Initial is 20.
Guys, 137.
Initial is 20.
What?
And then what's the second one? Velocity.
So we were right.
And then the next one is
No,
two.
we got a different number.
Your velocity is
And
5.
as you start the graph, remember you always graph in a specific order. First acceleration, then velocity, then position.
At -5, 10.
I think velocity.
No, I know what we did wrong.
So from 20.
Guys,
Okay, so at -5. Wait. So
No, it's the first one is up here at 20, right? Because that's the initial velocity in the first 5 seconds. And the next one would be 5.
so it's like here. Does it start at the origin?
Right? And then this one's like 1/4 of this
Okay, why is it the origin? Yeah.
velocity.
Because at the beginning, your velocity was
It was a positive. It's positive, so it can go up. And then, right?
why is it 135? Nash, why is it 135? It's 137.
Because that's what 100 minus 62.5 is. And that's what
Right, and then it went down to
So, not there. If you calculate it, you get
It's at 20.
the
And it's just
position
the origin.
at 5 seconds. It ends up being
with the initial velocity.
Sorry,
the position of
and then 0 to 5, where does it go? 0 to -5.
Why are you trying to go?
I think that's why.
Oh, we have to add 100 to it.
Why?
Because it's not 0 the initial
velocity.
Oh, yeah.
Right, we just don't have to add that.
So you forgot to add that. I'm sorry. I'm
This is what it was before. It's this. It's this. And then
Anything that
this
I say, I mean it is.
-5.
The one where Shannon Park pizza all over me. Fifth grade party.
But it was like moving in here.
So it goes down like this.
It's like they
The
were
ice cream sundaes were so good.
Down to this one.
I'm thinking of ice cream sundaes. Wait, what are we talking about?
This goes down to -1.
What's wrong?
the one you got the velocity.
Why is that wrong?
Constant velocity. Remember, it made a point of saying that.
So,
So it started here and it goes over.
why?
How do you graph the position?
First constant velocity, like the first 5 seconds.
They made me white out. I got white out.
Yeah, constant velocity.
And then after that, it's I'm on a roll.
How do you figure that out? This part. What is that?
The acceleration.
Is that that's the velocity decreasing at -5? Oh no, it goes to -5.
Well, it goes, yeah, but also first of all, it goes to -5, and then also the slope. The slope is -5 also.
Because of the
Acceleration.
deceleration.
Yeah, because the acceleration.
Constant velocity.
Cool, bro.
Cool.
Alright, and then,
Yeah, like that.
so,
Because this one, it goes from
who we have to find out across the access?
Who are you?
Alright, so, we put 0, no.
Wait, we're on position, no?
Put 20.
So at 5?
On the start, lay it out, it's like, oh, you're check it as you go. I'm trying to keep you guys a little bit ahead.
Oh, wait.
B equals what?
B equals V naught plus 8. So B equals -10, right?
Acceleration. Then there's no,
B naught is up.
I meant 7.
so what kind of graph is this?
Where did we get 0 from?
Isn't that what you're doing?
So 0 equals,
Oh my god. Can
20
you read this?
plus
So bad. You
0.
need to take more breaks.
B
Which equation you put it into?
Wait, no, it can't be 20.
You plug it in, sorry.
Makes no sense. I mean, it can't be 20. That position, it could be 25 and 10.
Okay, there we go. Which one are you talking about?
Which equation do you put 0 into? You not even take plus AT?
Yep. Except this time you know everything except t.
Right.
So
And also instead of
negative
putting
20
t, you
divided by
put like t minus 5 instead of
10.
because then you'll end up
Now just calculate t as I did in my example, and interpret your answer from that equation.
Yeah, Nash.
or you can do that. I mean, you get pretty much the same.
It's true, but it's a little bit easier to picture if you just calculate it and then relate it to the 5 seconds.
So we get 10 seconds. You get t equals 10.
No, not only it should be 10. Just
It's
imagine.
between 5 and 10.
Oh, that doesn't make sense. What did I do wrong?
Negative 20 equals negative 5.
Oh, that's 4. I just totally divided wrong. I'm so sorry.
4 from
So 4
5,
seconds. So what is what would you label it on the axis?
which is 7.
I would.
So you calculated 4 seconds. So how would you label that on the axis? Where is it? What is that?
So when you calculate where it was,
Yeah.
so
What is that?
V naught for this equation. Yeah, it's 9.
I'm so sorry. I'm just really tired of not thinking properly at all. Point of inflection.
This reminds me of calculus though.
What is it?
This is calculus.
Point of what?
It's
Well, the
calculus.
answer, like what it,
Yeah, what's the
and like
answer?
what it means to you is
Yeah, what does it
on
mean?
a metaphysical.
No, what's the answer? What does he mean? What is it on the graph?
Oh, it's a.
You just add 4 plus 5, which is 9.
I just looked at
So I get that.
I should have known that.
Because this was 5 seconds after 0. This was 4 seconds.
Why am I adding it
It's
to
at 100
5?
at 5.
Why did I add it to
Is
5?
that true?
Do you understand how I got the 4 seconds first? The reason why that this is 9 is because this is when I started keeping track of this. So you think of this as just 4 seconds.
How do you figure that?
Okay, so
Like infer?
This is like that's
Yeah, that's good now.
Like a slower rate.
So I calculated it like this.
So, yeah, but
Negative.
you.
Alright,
Oh,
I wasn't
interested.
interested.
So are you just
Wait, so how'd you get 9?
taking it? You're just taking it away from the graph.
I'm not gonna cheat. I'm not cheating.
I see.
This is
No
my
numbers.
My brain is just
I mean, this is a number to like get.
I can't. I don't want to write it wrong and then get confused later.
I know. My brain. Okay, thanks. You know what, Nash? You're over there correcting your line drawing. I'm just like trying to draw lines. 0. I feel
Hardest part of this process is
I got that, but
Ooh, 100.
what numbers tell you that what the
I got this. I understand. I understand.
I know I finally understand.
no.
See the line? Yeah, it is. Yeah, it is.
It's not long.
Why isn't it? Whatever.
Yeah, but it goes. But the highest point is when it crosses the axis at 9.
And then after that goes a little bit down.
Yeah, I know.
Okay, so what's wrong? My graph looks exactly like Nash. Tell me I'm wrong.
His goes down. You're wrong. $5.
So you've
What's
seen
wrong
this
with my
before.
graph?
You saw it just as functions before,
You go like
not really in the context.
and like that at 9 is your output.
Oh, apologize. So
And then you hit
It'll
rock
be
bottom.
$5.
I didn't think that.
We never agreed to that.
Okay. I have to like fight this out.
Exercise is hard.
Nash showed me about how to interpret that graph into that one and what makes the slope and the whatnot. It's like, but what numbers show you the way?
Well, the numbers would be kind of like this.
Why does this point go at
This guy right here is a constant.
same reason?
No, 9 is a high point and then
What's the derivative of the constant? Because that's how you would show it as actual equations. We'll get to that like at the very end of the chapter.
oh yeah.
It's just a constant or like
Oh, you can have this back.
You use my calculator?
Like once.
Clearly, that was really big.
I have Allie.
Yeah, that was the whole thing that's going on.
Don't get me sick.
What?
Don't get me sick.
Pass me your water.
Do we know what number 9 is?
So why is it linear? Shouldn't it be parabolic? Well,
Like,
acceleration.
do you know what value? That's what we have to find out.
So there's no quadratic terms, you just do this.
Yeah.
Which is the equation.
Where is
Have
the
you drawn the
vertex?
position function graph?
Oh yeah, and what value
And
is the
defining it
vertex?
correctly for the rest of it.
Okay, so
Well, that's not a vertex.
x0 doesn't matter.
Oh wait. Oh yeah, that's I was thinking of other like this.
Come on, just sketch it, just sketch it.
Which x0 do you use?
Is it position called x of x?
You don't know. So, because we don't know.
Well, I mean, based on my calculations and how the equations work, we have a general idea of what's
Good over there, Henry? How do you do the section graph?
But if you drew a sketch 5, then on 9, it doesn't go down.
Serenade me. Friends with Charlie Davis. That was kind of sad.
No. It's like
He's too old for you now.
one of the people who I was like friends.
Yeah.
I talked about the house was there like third grade. No one knows. I like friends. I'm not. That's never
So
happened.
in this case, the second interval is
Like
crap,
internet, like
the
a
acceleration is
every day.
negative 5 meters per second squared. The acceleration is negative in the very first equation of the top. The quadratic term is negative.
You don't even
Term
have
of math, the quadratic term is
to know each other
negative.
all the way.
Because the acceleration is 0, so there's no quadratic.
Yeah, I know his brother.
Yes, okay, this part, the second part.
So
His brother.
okay, so you can put it this. Positive, so it's
Yeah, I don't know. It's just like you have such a long
One turns negative.
No,
You're
it's
still positive.
No, we need a negative acceleration. We do end up with it. At the very end of the problem, the object is moving, yes, so let Notice that I've got the bulk of the problem up, there's only one last step.
plus b0, which is 5. 20 times 5 was 20 times 5.
100.
100.
How is that possible that that's the hypotenuse?
Plus 1/2 t squared. No, that's a thought.
That's the one final.
What are you plugging in? You're plugging in the same thing except for that.
This is after 4 seconds.
See, I would plug in 9.
That's the remainder of the problem. So take a look at the complete solution here now for a couple of minutes. Work it out amongst yourselves, then I'll run through the solution here briefly with you in a couple of minutes.
Kind of could do that, but then that would be, you have to do like a couple more steps. But like it's easier to just, because you know what it is at 5, so it's easier to start with that.
x0, wait, okay, can I see what you did? Can I see what it is?
How long are college meetings? When the colleges have how long?
I don't know.
I thought you went to one.
We didn't.
We left. The lots of them it was like half an hour.
So that's why I plug in 4 seconds. I can't plug in 9 seconds.
When you play that song, you did.
I like this better than this one.
No, I don't. I felt super smart when you signed astronomy stuff.
Because you have to think of this time interval all by
Astronomy stuff.
I like this more because mine had
It's
projects.
different.
I was like,
Oh my
Why
god.
would you like that?
Plug in
I
9
worked my ass
equation
off
that
on
would be
this,
completely
so
wrong. It would actually be 9 seconds.
nothing.
What'd you get?
5, it would be 14 seconds.
Final.
I got an A and then a B.
You look at the second.
Because I didn't get to use my tutor over final.
You didn't fail, did you?
But I like understood everything
Yeah,
going on.
okay,
I
that's
just didn't test well. So, like,
All right, let me take you through the complete solution. Kids in the 4th row, I need you to just turn around, please. Okay, let me take you through the complete solution here and then we move on. Okay, most of you, as I was watching you work on the problem, were able to pretty quickly calculate out the values here for the 2 intervals. graph out the acceleration as a function of time pretty quickly. That's usually the case. This portion of the problem up to here is usually pretty easy to do. So once again, for the first 5 seconds, there's no acceleration. For the remaining 5 seconds, it's a constant negative 5 meters per second squared. And then we start graphing velocity as a function of time. Notice immediately how this problem is a little bit different than the example that I did, in the sense that for the first 5 seconds of the problem, you have a constant velocity here of 20 meters per second. Once again, here's where the idea of the derivative comes in. Notice that the slope of the ruler's edge here is always equal to 0. That's this instantaneous acceleration here. Literally, this right here is the derivative of this. And then, over the remaining 5 seconds, our velocity goes from 20 meters per second to negative 5 meters per second, where right here the slope of this line is our acceleration of negative 5 meters per second squared. That's this quantity right here. But then, like in the example that I did, this line crosses this time axis. When that happens, it's going from a positive velocity to a negative velocity. At this instant, it has a velocity of 0, and we have to figure out when that happens. We have to figure out when that happens because it's our turnaround point. Now, the way that we calculate that is to do the following. Set the velocity v equal to 0, and then you have v equals v naught plus at, and you solve for t, which gives you this expression here. And then the values are this. It's negative, and then 20 meters per second for v naught, divided by negative 5 meters per second squared, gives you 4 seconds. But you have to realize it's 4 seconds after we started this process. 4 seconds after 5, which is 9 here on the axis. And then lastly, usually the trickiest part is getting the position. We first of all go from 0 to 100 meters in the first 5 seconds of the problem. But notice that this is not a parabola, it's a line. The reason why it's a line is because if the acceleration is 0, there's no quadratic term here in the position equation. This portion of it right here is linear. Once again, you can also understand that in terms of the derivative. Notice that the slope of the ruler's edge here for the first 5 seconds never changes. It's this constant 20 meters per second. This right here is the derivative of this line. And then for the remainder of the problem, the last 5 seconds, the acceleration being negative means that the quadratic term of your position equation is negative. If the quadratic term is negative, you end up with a parabola that opens downwards. We do hit a vertex right here in 9 seconds for the following reason. Right here, the slope of the ruler's edge is 20 meters per second. And then right there at the vertex, the slope of the ruler's edge is equal to 0. That's the velocity here when we're crossing the axis. And then we go from a velocity of 0 to a velocity right here at the very end of the problem at negative 5 meters per second. So the derivative of this parabola right here is this line. And then the last step is to figure out where that vertex is on the position axis. So you start right here. X naught is 100 meters. The v naught right there, remember, was 20 meters per second, and the acceleration is negative 5 meters per second squared. The common mistake to make is to set the time equal to 9 seconds. No, you set it equal to 4 seconds. 4 seconds after this process started. Take these values, plug them into the position equation. You end up with this 140 meters. That's the position here at the vertex. Yes?
If the second graph, it's a straight line for that like 10 meters, that means that the graph is
If it's a horizontal line on the velocity versus time graph, then on the position versus time graph, it's linear. It's always the way it works out. Once again, you can show the motion in this problem in the following way. I start at the origin while moving at a constant speed in that direction, 20 meters per second. Then after 5 seconds, I slow down and stop, turn around, and the problem ends when I'm moving in that direction at 5 meters per second. That's the entire problem. Okay? Okay, put this aside, please. Number 2 is for you guys to do on your own as homework. Let's move on. At this point, let me do some erasing. Yep. That was our break. That was our break. Take a nice deep breath. Slowly erase
Out after this.
Slowly erasing.
Like the face I drew between my brain.
You'll notice that I've turned the screen off.
I do that with my brain.
Slowly erasing.
That's like college. You don't want to see it.
Right now. Lie down, please. Listen up. Yeah, I know it's blisteringly hot, but you have to be like me. You have to just completely ignore it. There's nothing you can do about the weather, so why bother complaining about it? Just completely ignore it. That's what I do, and I'm perfectly fine, as dressed as I am. Who cares? Now, we've seen that these one-dimensional kinematics equations for constant acceleration are perfectly adept at describing people walking back and forth in front of desks, cars going back and forth on the road, people on bicycles, blah, blah, blah. But frankly, so what? That really doesn't tell us all that much about nature. What is physics ultimately concerned with? It's coming up with elegant, simple descriptions of nature. And now we once again get to Galileo. Now, prior to Galileo, with respect to motion near the Earth's surface, remember that the ancient Greeks, essentially what they thought of that motion is summarized into two statements. Heavier objects fall faster than lighter objects, and all moving objects eventually come to rest. I mentioned at the time that yes, Galileo experimentally shows each of those statements to be incorrect. With respect to the first statement, Galileo makes a realization about falling objects that everybody here in this room today takes for granted. He rightly considers that when an object is falling through the air resistance acts upon it. Air resistance, in other words, slows down falling objects. Now, of course, we take that for granted today. That's not a very strange idea. 400 years ago, he was literally the first person to think of that notion and conceptualize it. So Galileo realizes that air resistance slows down falling objects. So then he asks the following question. What would happen to a falling object in the absence of air resistance? Now, by asking this question, Galileo conceives of the idea of a vacuum, a region of space where there was no air. In other words, what would happen to a falling object if there wasn't any air? That's an easy concept, of course, today for us to grasp. Just picture the airless surface of the moon, for example. But once again, 400 years ago, that was kind of a difficult concept for people to grasp. How could you have a region of space where there was no air? And if there was no air, what would then happen to a falling object? Galileo essentially asks this question. And then he devises a very simple experiment to answer this question. Remember I said a little while ago that Galileo was given a great deal of credit with the development of the scientific method because around the same time, he and a few other people did comprehensive experiments to answer questions such as this. Now Galileo's experiment, it turns out, I'll describe it for you and demonstrate it very easily, is very simple. What Galileo does in a very simple primitive laboratory is he takes an inclined plane, slope for example, like so. Then he tries to make the plane as smooth as he possibly can to, over a short distance, mimic a frictionless surface. So no, he couldn't produce a vacuum in his laboratory. He could only envision one and approximate it as best he could. And then what he did was he took an object, set it onto the incline, and he then just released it from rest. And then using the kinematics equations, which he himself derived, he was one of the first people in history to actually derive the equations, he measured the acceleration. And now here's was his experimental result. Regardless of the weights of the objects, all of the objects have the same constant acceleration. Regardless of the object's weight, the objects all have the same constant acceleration. This was his experimental result. Now, as I said, the experiment itself is fairly simple. Literally, all that he did was the following. He took an inclined plane, so tried to make it as smooth as he possibly could, took an object such as this eraser, placed it on the incline, released it from rest, and then measured the acceleration. Regardless of the weight of the eraser, his experimental result was that the acceleration of the objects was all the same number. And then what he did was he repeated the experiment, but in this case he took the inclined plane and he increased the angle of inclination. And then he did the same thing. He got the same result. All the objects, regardless of their weight, would have the same constant acceleration. It was a bigger acceleration here at a greater angle of inclination than, say, here at a shallower angle, but the result is the same. Now, based upon this result, what can you conclude? Well, if you took the inclined plane and tilted it such that it was completely vertical, and there's no friction, in other words, there's no air resistance, what would then happen to all objects regardless of their weight as they fell? They would fall with the same constant acceleration. What Galileo discovered here is referred to as free fall. An object in free fall falls with the same constant acceleration regardless of its weight, as long as the effects of air resistance have been removed. In other words, he has experimentally overturned the ancient Greek idea that heavier objects fall faster than lighter objects. That's completely incorrect. Instead, all objects, regardless of their weight, fall with the same constant acceleration once the effect of air resistance has been removed. All objects, regardless of weight, fall with the same constant acceleration, speed, acceleration. Once the effects of air resistance has been removed. Now, as I said, Galileo couldn't actually conduct or construct rather a vacuum in his laboratory. He could only approximate one very primitively and envision the idea. But let me show you a more modern version of Galileo's experiment. Do something following. I have here in this tube two objects, a penny and a feather. And right now there's a lot of air inside the tube. So then therefore, yes, of course, there's going to be a lot of air resistance acting on the feather. Notice, of course, that the acceleration of the feather is a lot smaller than the acceleration of the penny. However, by means of this vacuum pump, I could actually remove most of the air from this tube. This would have amazed Galileo 400 years ago. 400 years ago, he certainly couldn't produce a vacuum in his own laboratory. He could only envision the idea and mimic it as best he could. But by means of this vacuum pump, even after just a few seconds or so, it turns out that he could remove most of the air from his tube. And then after I remove most of the air from this tube, then you will find that the acceleration of the feather and the penny are the same, even after just a few seconds. I got stuck. Even after just a few seconds, notice that the acceleration in the feather and the acceleration of the penny are more and more becoming the same number. So once you remove the effective air resistance, as Galileo correctly discovered with his experiment, all objects fall with the same constant acceleration. So, okay, now I'm going to turn the pump off, and I'll remove the hose, and when I do, you can hear the air going back inside the tube. Like so, and now all the air resistance is back in the cell, and on the feather. Galileo, in fact, was correct. That's your first physics demo, by the way. A lot more fun.
Exactly. What would it feel like to just be like, is there anything like?
Because this acceleration is so important in describing motion near the Earth's surface, it's given its own symbol. This acceleration is referred to as small g. Small g is not gravity. It is acceleration due to gravity. It was first measured by Galileo as he conducted his experiments almost 400 years ago. In metric SI units, it's equal to 9.8 meters per second squared. If you convert that number into English units, it's 32 feet per second squared. This was originally measured by Galileo as he conducted his experiments. You yourselves, by the way, next time in class, as part of your first formal laboratory exercise, will measure the value of g, the acceleration of your gravity. Henry?
Is there any matter inside that when you take it out?
Now, there's still a little bit of air inside the tube. Okay, I can't remove all of the air from the tube itself by means of that simple vacuum pump, but I can certainly get most of it out. And if I can get most of it out, as you saw, the acceleration of the penny and of the feather are becoming more and more the same number. If I can remove all of the atmosphere from the tube, then yes, I would find that all of the objects accelerated at the same rate, 9.8 meters per second squared.
How come I remember in calculus
You saw something called 1/2 times g. You'll see that pop up in the equations in just a few minutes. Okay, now at this point, let's clear up some misconceptions that you may have had about an object in free fall prior to coming into this class. For example, let's say that I take an object and I just drop it from rest. If we ignore air resistance or if we remove the effects of air resistance, then regardless of the weight of the object, it will fall not at a constant speed, but with a constant acceleration of 9.8 meters per second squared downwards. If I take the object and I throw it downwards, like so, while it's in my hand, it's not in free fall. However, the instant that I let go of it, once again, if we ignore air resistance, such as only under the effect of the Earth's gravity, then it accelerates downwards at 9.8 meters per second squared. And that's relatively straightforward. Usually what trips everybody up, however, is describing what happens if I initially take the object and throw it upwards like so. While the object is moving upwards, is it still accelerating downwards at 9.8 meters per second squared?
Yeah.
Yes.
Absolutely. There's nothing different about the Earth's gravity while the object is moving upwards as opposed to moving downwards. If you're having trouble wrapping your head around that idea, just think of it like this. If I initially throw the object upwards like so, I give it an initial velocity vector of v0 that looks like this. However, as it moves upwards and slows down at any moment in time, its final velocity vector v would look like this. Using the tail-to-tip method of vector addition, notice in which direction the change in velocity vector delta v points. So, remember that initial plus change is equal to final. And remember that the direction of delta v and the direction of the acceleration is the same. So as the object moves upwards and slows down, the acceleration vector is downwards, and the magnitude of it is 9.8 meters per second squared. The easiest way to think of that is just remember, there's nothing different about the Earth. There's nothing different about the Earth's gravity while the marker is moving upwards as opposed to moving downwards. The whole time the acceleration is downwards in 9.8 meters per second squared. Okay, now, the equations that we've been working with. in the last period and a half, talking about bicycles and cars and blah, 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 the one-dimensional motion equations with constant acceleration, they now apply in this all-important situation for an object in free fall, explaining this very important motion near the Earth's surface. However, when we write the kinematics equations for free fall, we rename things slightly. The equations are written like this. Okay, of course, now here's how we saw our expressions. First of all, position equation, velocity, and then also the third kinematics equation. When talking about the situations that we've already described, we've always thought of that motion as occurring along a number line that was horizontal. So then we just think of that as the x direction. In this case, for an object in free fall, the motion is vertical. So instead of thinking of that as the x direction, we just think of the vertical direction as the y direction. And then the next thing that we change is the acceleration. The acceleration is always the same number for an object in free fall. It's g downwards at 9.8 meters per second squared. By definition, we think of downwards as the negative direction and upwards as the positive direction. That then causes these equations to be named in the following way. Okay, first of all, the position equation is now written like this. Here's your 1/2 g. So, this is the exact same equation as this, except we now think of position, initial and final, in terms of the y direction, and the initial velocity is now rewritten slightly as well. This is pronounced v(y naught). This is the initial velocity in the y direction. And then notice what happened to the plus 1/2 at squared term. The acceleration is always the same number now, 9.8 meters per second squared, and it's downwards, hence the negative sign. We think of downwards as negative and upwards as positive for simplicity. Okay, similarly, the velocity equation is renamed a little bit. The velocity equation is written like so, where it's the exact same expression as before, but now this is the initial velocity in the y direction. V sub y, as we say, is the final velocity in the y direction. And then plus at is written as minus gt, with the acceleration the same for everything, and downwards is the negative direction. If you algebraically combine these equations together to get the third kinematics equation, it appears like this. So, in this free fall form, that's the third kinematics equation. But before we go any further, we're actually manipulating these expressions and so on in examples and doing our laboratory exercise next time in class. Once again, we got to try to clear up everybody's misconceptions about an object in free fall. The easiest way to clear up your misconceptions is to graph out position and velocity as functions of time, just like we did today in example problems, but now just specifically for this case of free fall. In order to do this process most simply, let's just assume that the object starts the origin. So let's just set y naught equal to 0 for simplicity. And then we'll consider three situations. An object dropped from rest, an object thrown downwards, and an object thrown initially upwards. The first two situations are pretty simple and straightforward. Let's see what happens first for an object dropped from rest. Now, if an object is dropped from rest, just simply so, what is the initial velocity of the object? Yeah, 0. So if the initial velocity of the object is 0 and the object is dropped from rest, we write that as v(y naught) 0. First, let's actually graph out its acceleration as a function of time. For an object in free fall, the acceleration as a function of time is always the same thing. It's always a constant, a horizontal line like so. specifically with a value of g, 9.8 meters per second squared, downwards, however, in a negative direction. It doesn't matter if the object is dropped from rest, thrown downwards, or is thrown initially upwards. For an object in free fall, the acceleration as a function of time always looks like that. And then next, the velocity as a function of time. The velocity as a function of time is always the same line. It is specifically a line with a slope of minus g. The only thing that will change in my situations is the y-intercept, the initial velocity. So if the object is dropped from rest, then the velocity as a function of time, that graph, merely looks like this, where it's once again a line with a slope of minus g. And the object is dropped from rest, right here, the y-intercept, the initial velocity is 0. So then, therefore, all that happens is that the object speeds up in the negative direction after you let go of it. And then lastly, for this situation, would be position as a function of time. It's always the same parabola. The parabola always opens downwards. The only thing that changes from these situations is where is the vertex. So if I graph for an object that is dropped from rest, position as a function of time, the parabola merely looks like this, where right here at the origin, that's where the vertex is. The reason I know that has to do with, once again, the derivative. Think of it like this. Right here at the origin, where the vertex is, notice that the slope of the tangent line, the ruler's edge is 0. And that's the instantaneous velocity is 0. Right here, times t is equal to 0. And then our velocity goes from 0 and just gets increasingly more and more negative. It's increasingly more and more negative as the object falls. Okay, that's pretty simple and straightforward. Next, the object is thrown downwards. If the object is thrown downwards, once again, to clarify, while it's in my hand, it's not in free fall. The instant that I let go of it, then yes, it is in free fall, and its initial velocity is a negative number because I throw the object downwards in the negative direction. So the object thrown downwards. V1 is now a negative number. If we graphed out the acceleration as a function of time, it's exactly the same. The object is still in free fall. If I graph out the velocity as a function of time, it's the exact same line with a slope of minus g, and now the y-intercept is just a negative number, which is like this. So, right here is our slope of minus g. Right here is the y-intercept, v1 which is a negative number. If we graphed out the position as a function of time, it's the exact same parabola as before, but the vertex is no longer at the origin. Instead, it looks something like this. And like so. It's like we're further along in the parabola as our starting point. Once again, the reason I know this has to do with the derivative. If you take a look at the slope of the ruler's edge right here at the origin, notice that it's a negative number. That's this negative initial velocity. And the object simply speeds up as it falls in the negative direction. So you may want to note here that this is not a vertex. Once again, these two situations here are fairly straightforward. What always trips everybody up, however, is understanding what these graphs look like and why they do for an object that is initially thrown upwards. So now for an object that's thrown upwards, such as the marker, like so, what could you say about the initial velocity v1 now? It's a positive. So v1 is now a positive number. Once again, if you graph out acceleration as a function of time, it's the same thing, which is downwards at 9.8 meters per second squared. If you graph out the velocity as a function of time, it's once again the exact same line with a slope of minus g, and now the y-intercept is a positive number. The graph now looks like this. so. Once again, it's the same line as before, with a slope of minus g. And right here, the y-intercept is the initial velocity, which is a positive number. It's usually this graph right here that confuses everybody initially. Think of it like this. What is the object doing on this portion of the line? It's moving upwards and slowing down as it does. And then right here, its velocity is 0 when the object reaches its maximum height. And then it falls downwards in the negative direction, speeding up as it does. The whole time its acceleration is downwards, the slope of that line, at 9.8 meters per second squared. Now let me ask you this. For how long of a period of time is the marker at its maximum height? How long is it there?
0 seconds.
Literally an instant, a non-measurable amount of time. Now, you may be having some trouble wrapping your head around that, but imagine that the marker, when it reaches its maximum height, is at that position for a measurable amount of time. What would this graph look like? What would it look like this? Don't wrong. It would look like this. So here's the velocity as a function of time. Then the marker moves upwards and slows down as it does, and then it reaches its maximum height. And then it stops. And it decides, just by itself, to stay there for a while, like so. And then, just by itself, then it decides to fall down. Like so. This is, of course, not the physics of the real world. This is the physics of perhaps the Warner Brothers cartoon world. How many of you remember watching Wile E. Coyote and Roadrunner? What happens when Wile E. Coyote, as he's chasing the Roadrunner, goes off the cliff? He doesn't fall immediately. He stays there for a while like so until he notices that he's over the cliff, and then he decides to fall down like so. That's the physics of the Warner Brothers cartoon world. That is, of course, not what really happens. Literally, the object is at its maximum height for a non-measurable amount of time, for an instant. And that's it. Is the position as a function of time. It's once again the exact same parabola as it was before. It's just that now the vertex is in the first quadrant of this graph. Now the parabola. It's like this. Once again, you can understand that in the context of the derivative. Ruler. Right here at the origin, notice that the slope of the ruler's edge here, the velocity, positive number. And then the velocity goes from a positive number to 0 at this instant when the object reaches its maximum height. And then it goes from 0 to a negative number like so, as the object falls downwards and speeds up as it does. That's all there is to it. Okay, let's take a look at the board. That's as far as we go today.